So in this video we are going to discuss the question in thermal and statistical physics which appeared in CSIR December 2014 examination. So let's continue with the first question. The statement is the pressure P of a fluid is related to its number density rho by the relationship by the equation of state which is given as this expression, okay, where A and V are constants. If the initial volume of the fluid is V naught, the work done on the system when it is compressed so as to increase the number density from an initial value of rho naught to rho naught is given by, okay. So here we are going to make use of the fundamental definition of the work done, okay. So first of all, let's try to write the equation of state, okay, which is given as P, that is equal to A rho plus B rho square, okay, where A and V they are given to be constant and rho is the number density, okay. So rho, that is equal to number density, number n by B basically, okay, in general. Now the work done on the system, because it's a work done on the system, so by convention we are going to take it as a negative quantity. So the work done on the system is given by W. So by convention we are taking it as negative quantity minus P dV, okay. So here we will substitute the equation 1 for P, and then we will see that how this equation is transformed. So that is equal to minus outside and then inside the bracket. So because it's a variable is volume, so we will write rho in terms of V, okay. So that is minus A, the first term, A n upon B dV, that's the first term, okay, and then plus B plus second integral B rho square, that is B n square upon B square dV, okay. So that is the expression for the work done, and after which upon integration, if we assume that volume changes from V1 to V2 and here also V1 to V2, so then upon integration we obtain minus outside AN and then V1 to V2 dV by B plus again the constant term outside and then dV upon B square B1 to B2 and then close the bracket, okay. So this is equal to minus AN ln V2 upon V1 plus Bn square, and inside the bracket it's minus 1 by V, and then we will apply the limits of integration. So the minus 1 by V and then upper limit, so minus 1 by B2 and then minus plus upper limit minus lower limit, okay. So plus 1 upon V1, this one, okay. So this is equal to, so okay, so before we evaluate this quantity, so let me call this as equation 3. So because the volume is changing from okay, so we are given that the number density changes from when initial value rho naught to rho naught, okay. So that means the rho naught is given as n by V1. So this implies V1 is n upon rho naught, that is equal to V naught, let's say, and 2 rho naught, because it's changing from rho naught to 2 rho naught, and that is equal to n upon V2, implying that V2 is equal to n upon 2 rho naught. So therefore from V1 and V2 we obtain B2 upon V1, that is equal to n upon 2 rho naught into rho naught by n. So this will cancel, that is equal to 1 by 2. So we will substitute B2 by B1, that is equal to 1 by 2. So therefore equation 3 reduces to, so W is given by minus an ln 1 by 2 and an ln 1 by 2 plus b n square, and then B2 is, so here I am writing 1 upon B1 first and b n square, and 1 upon B1 minus 1 upon B2. Okay, so 1 upon B1 will be equal to rho naught by n. Okay, so rho naught by n minus 2 rho naught upon n. Okay, so this upon solving, so this will give us an ln 2 plus bn rho naught. Okay, this is equal to a ln 2 plus b rho naught multiply by n, and n is equal to rho naught. So n, that from here, from this equation, n is equal to rho naught v naught. Okay, so that is equal to a ln 2 plus b rho naught multiply by rho naught v naught. Okay, so that's the work done. Okay, so that's our final answer. So therefore it is a plus a ln 2, no, this is the option D here. Okay, so therefore option D is the correct one here. So let's continue the next problem. The statement is, an ideal Bose gas is confined inside a container that is connected to a particle reservoir. Each particle can occupy discrete set of single particle quantum state if the probability that a particle quantum state is unoccupied. Okay, then average number of boson in that state is given by how much? Okay, so occupation number for the boson, we know that it is the occupation number, that is equal to 1 upon exponential beta E minus mu minus 1. Okay, where mu is the chemical potential. So we are given that the probability that a particular quantum state is unoccupied. Okay, so for unoccupied state, we can write 1 minus occupation number, which is nk. So basically this function gives the occupancy of particular state. So 1 minus occupation number, that's this information given to us, that is 0.1. Okay, so from here we can rearrange this equation. So occupation number n, that is equal to 1 minus 0.1, and that is equal to 0.9. So that means this is basically 9 divided by 10. So this says that 9 out of 10 boson will occupy the given state. So this implies 9 out of 10 boson will occupy given state. Okay, so therefore right option is B here. Let's continue with the next problem. The statement is, in low density oxygen gas at low temperature. So that means we are talking about the low temperature, only translational and rotational modes of the molecules are excited. The specific heat per molecule of the gas is given by, okay, so it's an oxygen gas molecule and at low temperatures. We know that oxygen gas, it's diatomic in nature. Oxygen, it is diatomic. Okay, so if a diatomic gas molecule is moving, it will have 3 translational degrees of freedom. Okay, so now because we are talking about the low temperature, so only the rotational degrees of freedom they will come into picture, and we need not worry about the bifacial degrees of freedom, because the bifacial degrees of freedom they become active only at by the high temperature. They are active only at high temperature, which is much larger than 1000 degrees Celsius. Okay, so now we are, let's try to understand that how many rotational degrees of freedom we should count for the diatomic gas molecule. So for this purpose, I will draw the coordinate axis, and we will line the gas molecule along one of the axes. So let's call this as x-axis, and this as y-axis, and this as z-axis, and let's say the molecule is lying along the z-axis. Okay, so now this diatomic gas molecule will have the option of rotation along the x-axis, along the y-axis, and also along the z-axis. Okay, so it can rotate about all these three different axes. Okay, so the rotational energy for this gas molecule can be written in terms of the corresponding angular momentum L1 along the x-axis, and also the moment of inertia. So here L1, it corresponds to angular momentum, and I1 is the moment of inertia along x-axis. Similarly, we can assign the value I2 and L2 along the y-axis, and also I3 and L3 along the z-axis. Okay, so with this information we can write the expression for the rotational energy of the diatomic gas mole E rotational, that is equal to L1 square upon 2I1, that's the rotational energy along the x-axis, plus L2 square upon 2I2 plus L3 square upon 2I3. Okay, so here the point that we should note here is that the axis along which the gas molecule is lying. Okay, so along that axis, if you do the evaluation of the moment of inertia of the gas molecule along that particular axis, so then it will have a very small value. The moment of inertia is going to be small. As a result, this entire energy term it become a large quantity, and this results in that this mode cannot be excited at ordinary temperature. Okay, so if one cannot excite this mode at ordinary temperature, so that means this implies that neglect this mode of degrees of freedom. So neglect this degree of freedom. Okay, so therefore in for a diatomic gas molecule, so we will have only 2 rotational degrees of freedom. So here we will have only 2 rotational degrees of freedom. So we are asked the specific heat per molecule of the gas. Okay, so from here, because we are having 5 degrees of freedom, so the average energy per molecule is given as E, that is equal to the degrees of freedom multiplied by average contribution to the average energy by 1 degree of freedom, which is kVT by 2. Okay, so this is equal to 5 by 2 kVT. Okay, so that means the corresponding heat capacity per molecule, that is equal to ddt of E. Okay, so that is equal to 5 by 2 kV. So that's our answer. So therefore D is the correct option here. So let's continue with the next problem. The statement is a collection n of non-interacting spins. So we are having a collection of n non-interacting spin Si, where I can take value from 1 to n, and Si can be equal to +1 or -1 depending upon whether spin is aligned in the along the field direction or opposite of the field. It is kept in an external magnetic field V at a temperature T. The Hamiltonian of this system is given by H is equal to minus mu V. So let me write the Hamiltonian, which is given to us H, that is equal to minus mu V sum over Si. Okay, what should be the minimum value of mu V upon kT? What is so we have to figure out what is the mu V upon kVT. such that the average value of SI, that is greater than equal to 1 by 3. So we have to find the value of mu v by kt such that this condition is satisfied. Okay, so let's try to figure out how we can proceed or how we can solve this problem. So Hamiltonian is given to us, and since we are talking about the because this system is kept in an external magnetic field. Okay, so depending upon the alignment of the spin, whether it's aligned along the field direction or the opposite to the field, so we will have two energy interaction terms here. So E1, I'm calling this as, so we are continuing with one single spin. Okay, so E1, that is equal to minus mu b when spin is aligned parallel to field. Okay, and I'm calling that E2, that's the energy, which is equal to mu b when spin is aligned anti-parallel or opposite to B. Okay, so these are the two energy terms, and based upon these two energy terms, we have to look for the appropriate expression for the partition function. For the single spin, so that means single spin has two possibilities: either it can align along the field direction or it can align opposite to the field direction. And if I call that for this case, the corresponding value from assigning, let's say when spin is aligned along the field direction, S is equal to +1, and this is equal to -1 when it's aligned anti-parallel to the field direction. Okay, so now the partition function for single spin is given as that is equal to exponential minus beta E1 plus exponential minus beta E2. So now we will substitute the corresponding value of E1 and E2, and then we will obtain exponential beta mu b plus exponential minus beta mu b. Okay, so this is the partition function. Okay, now the average value of SI is, it's given as SI, that is equal to, so we will follow the standard definition of average of a physical quantity, that is SI pi. Okay, so and that is equal to SI taking value from -1 to +1, because it can take only two values, and then SI pi. Okay, and that can be further written as, it is when SI it's taking a value of -1, and then the corresponding probability corresponding to SI, that is equal to -1, and then plus SI is equal to +1, and then corresponding value of the probability P plus. Okay, so now we will try to find out the corresponding values of the probability. So let me call this as equation 3, or I can rewrite this as minus P minus plus P plus. So let me call this as equation 3. Okay, now the probability of the spin, the probability of spin parallel to field is parallel to field means, so that means we are talking about SI is equal to +1, and that probability we are denoting as P plus, that is equal to exponential minus beta, and the corresponding energy when spin is parallel to field, the corresponding energy is minus mu b, exponential minus mu b divided by the partition function Z. So that is equal to exponential beta mu b upon Z. Okay, similarly for the second case, when the spin is aligned anti-parallel to the field, so that means for spin anti-parallel to field P negative, so that means when anti-parallel to field means when SI that is equal to -1, so P negative, so that is equal to exponential. So now we will make use of this energy E2, exponential minus beta mu v upon Z. So that's the probability. Okay, so based upon expression 4 and 5 and combining it with the expression 3, equation 3, so the mean value of the SI, so that is mean SI, that is equal to, okay, let me move to the next page. So I will write it here. There, the expression for the mean value of SI that is equal to, if you just take a look at the final expression that we wrote, this is equal to this quantity minus p minus plus p plus. So while adding these two quantity, we are adding z common in the denominator. So I'm clubbing these two steps in a single step. So I can write the mean value of SI, so that is equal to minus exponential minus beta mu v plus exponential beta mu b divided by e power beta mu b plus exponential minus beta mu b. Okay, so since it is given that this SI value it is greater than equal to 1 by 3, sorry. Okay, it is greater than equal to 1 by 3. So in order to solve it, we will do the cross multiplication, and that will give us, after doing the cross multiplication, so we obtain 3 into e power beta mu b minus e power minus beta mu b, and that is equal to not equal to but greater than equal to e power beta mu b e power beta mu b plus e power minus beta mu b. Okay, or it turns out to be equal to 3e beta mu b minus 3e minus beta mu b greater than equal to e power minus beta mu b. So I have interchanged the term plus exponential e power beta mu b. Okay, or bringing the terms with the similar exponent on the one side, so we obtained 3 exponential beta mu b minus exponential beta mu b. So that will give us okay, so I'm clubbing this term and this term together on the left hand side. So this can be written as 2 exponential beta mu b. Okay, and that is greater than equal to, so taking this term on the other hand side, so this become 4 exponential minus beta mu b. Okay, and after solving it, so this is equal to 2 exponential beta mu b upon exponential minus beta mu b greater than equal to 4. Okay, so this implies, so 2 will cancel with 2. Okay, so that means this implies e power, so we club this exponent here in the numerator, so that means e power 2 beta mu b that is greater than equal to 2. Okay, so that means this implies that 2 beta mu b that is greater than equal to ln2. Okay, so therefore mu b upon kVt, so I am replacing beta with kVt, that is greater than equal to ln2 divided by 2. So that is the final answer. So that means when mu b by kT is greater than equal to ln2 by 2, so then that condition this condition is satisfied. Okay, so therefore our right option is C here, ln2 by 2. Okay, mu b by kt, the minimum value, so therefore the minimum value will be ln2 by 2. So therefore C is the correct option here. Let's continue with next problem. It is from the random walk article. The statement is, a random walker takes a step of unit length in the positive x direction with probability 2 by 3. So that means here if we call the probability of taking steps towards right, so if we call that as p, and that is equal to 2 by 3. okay, and a step of unit length in the negative direction with probability 1/3. So then the probability of taking steps along the left side, that is equal to 1/3. Okay, so this is toward right, okay, and this is toward taking a step towards left. Okay, now after n steps, the mean displacement of the walker after n steps, we have to calculate that. So after n steps, the mean displacement towards right is equal to n into p minus q. Okay, so that's a general result that we obtained when we talk about the random walk in one dimension. Okay, and that is equal to n, that's the total number of steps, multiplied by the probability of taking steps toward the right direction minus probability for taking steps along the left direction. Okay, so that is equal to n divided by 3. So therefore A is the correct option here. So let's continue with the next problem. The statement is, when a gas expands adiabatically from volume V1 to V2. So, okay, so we are given a situation where gas is expanding adiabatically from V1 to V2 by a quasi-static reversal process. Okay, so by a quasi-static reversal process, if it cools from temperature T1 to T2. Okay, so that means the first process here, it is quasi-static reversal process. Okay, and during this process the temperature changes from T1 to T2. Okay, and the second case is that when the same process is taking place by a adiabatically and irreversibly. Okay, quasi-static. Okay, so this is basically quasi-static reversible, but adiabatic also. Okay, it's given when a gas expands adiabatically from V1 to V2. So that means this is also adiabatic process. Adiabatic. Okay, in the second case again it is a adiabatic and irreversible process. And it expands from T1 to T2 dash. Okay, but the volume changes from B1 to B2 in both cases. Okay, now we have to find the relationship, that what is the relationship between T2 and T2 dashes. That is our objective. Okay, so the one thing that is common in this both of these two cases, these two processes, is that both are adiabatic in nature, and one of them is reversible and another one is irreversible in nature. Okay, so in both cases dq, that is equal to 0. Okay, so if we apply the first law, du, that is equal to dq minus dw. Okay, so because dq, this is equal to 0 here, so that means this says that the work done, that is equal to negative of potential energy. Okay, so let me call this as equation 1 here. Okay, so du, or you can say in other words du, that is negative of work done. A negative du mean what? Okay, because gas is expanding, so dw will be positive. Dw, it's going to be positive. This is by convention. So when dw is positive, so du, that's negative. A negative du implies du equal to negative. This implies that u final is smaller than u initial. The final internal energy is lower than initial internal energy. This implies TF is lower than T initial. So that means in both cases, whether it's reversible adiabatic process or irreversible adiabatic process, it will lead to the cooling. So in both of these two cases, cooling will take place. Okay, but now the question is, in which case the more cooling will be produced? Okay, so let's try to figure it out. Okay, so we know that for the same expansion volume, so please try to understand this point. For same expansion, for same level of expansion, that is, in both cases the gas is expanding from V1 to V2. Okay, so that means delta V is change, it is same in both of these two cases. Okay, so in this so therefore the work done in irreversible process is going to be larger than in a reversible process. Why? In a reversible process. This is an important point to note here. But why? Why the work done in an irreversible process for the same level of expansion? Why the work done in an irreversible process it's going to be larger than the work done during the reversible process? The point is that when we talk about the irreversibility, so due to the presence of the additional frictional forces, the system has to work against all those forces. So therefore, to achieve the same level of expansion, the work done during irreversible process, it's going to be larger than the work done during the reversible process. It is because to take into account the frictional forces. Okay, so that's the point here. So why? So here, so I will write dW irreversible, that is going to be greater than dW reversible. So because delta W, it's directly connected with the change in internal energy. So here rather than putting the sign convention, because basically we are talking about the magnitude only. Okay, so here I will write, so this will imply that delta U, the internal energy change during the irreversible process, okay, that's going to be greater than delta U during the reversible process. Okay, so because delta U and delta U it's connected with, so we can write du during a particular process, that is equal to NCB dt. So delta U is directly connected with the change in temperature. So therefore we can write with the help of this equation, we can write this inequality as dt irreversible is greater than dt reversible. Okay, let's switch to the next page. Okay, sorry, it's the next question. So let me introduce a page here. Okay, so from previous page we concluded that dt irreversible is greater than dt reversible. Okay, so that means this implies because dt irreversible is what? This is the final temperature that is achieved during irreversible process, that is T2 dash minus the same initial temperature which is T1 for both of these two processes. This is greater than T2, the final temperature obtained during reversible process, reversible expansion minus the initial temperature. So T1 will cancel on both sides. So this result lead to the conclusion that T2 dash is greater than T2. Okay, so this is our final answer. Okay, so let's see which option matches with our, so therefore B is the correct option here. But now let's try to understand it's from physics point of view, what's the logic behind this. Suppose our starting temperature was T1. Okay, let's say that was 30 degrees Celsius. Now we allowed these gases to expand in two different ways. One and both of these two ways, they follow adiabatic process. Adiabatic process, one is reversible and other one is irreversible. And when you talk about the irreversible process, so that means here the frictional forces, you need to consider frictional forces, and in order to overcome these frictional forces you have to work more. as compared to the reverse loop process, because reverse loop process, it's an ideal process here. Okay, so here let's say the final temperature that we achieve here, because T2 it's going to be smaller than T2 dash. Okay, so it's a reverse loop process. So let's say the final temperature that we obtain, that's 25 degrees Celsius, and here let's say it is 27 degrees Celsius. Okay, so why we were not able to achieve a larger a larger fall in the temperature in irreverse loop process? Because some of the energy has already been utilized to to take into account the frictional forces here. So here in this case, delta T is equal to delta T reversible, that is equal to 5 degrees Celsius in case of reversible, whereas in case of but what you call this as irreversible case, so it is 3 degrees Celsius. Does it make sense? Yes, it does make sense, because if you just take a difference between T2 dash and T1, so we obtain a value of minus 3 degrees Celsius. Okay, and if you just take a difference between T2 and T1, so a difference of minus 5 degrees Celsius is obtained here. Okay, so it doesn't make sense, because T2 dash minus T1, that's minus 3 degrees Celsius, which is larger than T2 minus T1, which is minus 5 degrees Celsius. So therefore our final answer is T2 dash, it's greater than T2.